Hello, good evening, everyone. My name is Aditya Sharma, and this is Fundamentals of Compressible Flow course being conducted by NPTEL, right? And in this uh, particular course, from the very beginning, we have been conducting these live tutorial sessions pertaining to mm, different weeks content for this course, right? So in this series, this is our 11th session, right? Pertaining to 11th week's content for this course, right? And the agenda for today's discussion will be measurement, diagnostics, and experimental facilities for compressible flow rate. So the instructor for this course, as we already know, is Professor Niranjan Sahu, affiliated to Department of Mechanical Engineering, IIT Guwahati. And I also am a research scholar, a PhD student, right? Currently under the supervision vision of Professor Niranjan Sahu only, right? Under his supervision only, I am doing my research work, right? So we shall wait for a couple of minutes, right? After that, we shall start today's session. Thank you. All right. So I believe we should start today's session, right? So, as I've already mentioned, the agenda for today's discussion is measurement diagnostics, right? So, if we wish to measure our flow of concern, right? So, in that case, how do we uh, perform the diagnostics of that particular experimental setup, right? And then what type of experimental facilities out of that we get, right? When we are trying to study our flow. So this has been discussed in this week 11's content, right? Right. So there are different techniques are there that have been discussed, right? For supersonic flows, right? And then for subsonic flows also, and the facilities, right, that have been discussed in this week's content, right? So we shall see that also, and questions based on that, right? So as we have been doing in these sessions, so the session goes like this. First of all, for a few minutes, we briefly discuss the topics that have been covered in the particular week's content, right? And after that, we move on to questions. First of all, we see some conceptual questions. So we have evolved this way, right? So first we see conceptual questions, and then we move on to numerical type questions, right? And later we then, with that, conclude the session of that day, right? So we shall, sorry, so we shall proceed in that manner only today also, right? Okay. So let's see the topics that have been covered in this week's content. So in total, there are three three lectures, right? Lecture 26 to 28. Okay. So also, I was watching the content of this course. So in the last video, in lecture 31, so Professor Niranjan Sahu has demonstrated the lab facility at IIT Guwahati, right? So it's a shock tube facility that professor is discussing in that video. So I recommend that the students who have taken this course must go through that video. It's very, in reality, they'll get a sense of how in reality the research goes as far as the compressible flows are concerned. So it's a shock tube facility, basically, and the instrumentation related to that has been discussed in that video. So I highly recommend that the students watch that video, right? So now coming to this session, right? So first topic in this lecture 26 is measurement challenges in compressible flow. Right. So briefly, this has been discussed that what type of measurements are required as far as the compressible flows are concerned. So one statement goes like this, that we need pressure and temperature data, all right, for that flow. Sorry. So in this way, the discussion has been done in that particular in this particular topic, right? Right. So it's basically an introduction to this whole diagnostics and experimental facilities uh, topic, right? Then there comes this temperature measurement, right? So how do we measure temperatures in compressible flow, right? So this has been discussed in this topic, right? So the device that we use to measure temperatures, we call it a thermocouple, right? So which is essentially the uh, two materials, right? So the heat that flows across these two different materials, so that leads to this EMF generation, right? Electromotive force, right? And from that we try to get sense of the temperature related to that, right? Based on that. So this is uh, this effect is named as Seebeck effect, right? Related to thermocouples, right? So a discussion has been done on that, right? And then there are in this topic there are a couple of subtopics. There are four subtopics in this discussion, right? So one such topic is the Prandtl number, right? So Prandtl number, if you see, is it is the ratio of mu by a, right? Nu, sorry. Prandtl number is, if you see the boundary layer theory book of author H. Listing, right? So in that you'll find this very well, right? So nu here is for thermal diffusivity, right? So if this Prandtl number is high, it means thermal diffusivity of the flow that we are that is the flow that is of concern. For that, the thermal diffusivity is high, right? And in case this value is low, in that case, we know that the thermal diffusivity is low, right? So in that book, this temperature profiles also have been given, right? So, but this discussion because doesn't I believe come in the scope of this particular, so we won't discuss that here, right? But it's a pretty interesting topic, right? So if someone wants to uh, read more about it, so one can refer to the book, right? Boundary layer theory by H. Listing, right? And then sorry, and then the next subtopic is adiabatic wall temperature, right? Which is nothing but when we are trying to measure a temperature at some wall, right? So in that case, if we keep this wall insulated, right? So there is no heat loss. In that case, the temperature we measure, the temperature we receive, right, from the sensor data, right, or the thermocouple data, that we call as adiabatic wall temperature, right? Then there are few recovery factors, right? So these are just to get a sense of how close our measurements are to the reality, right? And to correct that, right? So we have defined these recovery factors, right? So this adiabatic recovery factor is essentially the deviation in the probe reading and the stagnation temperature, right? Yes. So this is adiabatic recovery factor, right? And then the next subtopic is this probe recovery factor, right? So the expression for the probe recovery factor is, so later we'll have a numerical also on this, right? So I'll just, and also I apologize for the rescheduling of today's tutorial, right? Because of some unavoidable circumstances, so I had to reschedule or postpone in the session. Right. So, okay. So this probe recovery factor. Yes. So this probe recovery factor is right. So here T infinity, I'll just, is the static temperature. This is the total temperature, which we also call as the stagnation, right? Stagnation temperature. And then this is the mm, probe temperature, right? So in case we are using a thermocouple temperature, then the data from that thermocouple for the particular point where we are trying to measure our data, right? Measure our temperature, right? So this is probe recovery factor, right? And then there is next topic is pressure measurement. So uh, the different ways how we measure pressures, right, has been discussed in this topic. So, pitot static tube, right? So which is nothing but here we measure both uh, static pressures and stagnation pressures, right? So this is basically a L-shaped probe, right? So at the start of this probe, we have a hole, right? So from there we get the stagnation pressure, and at the walls of this probe there are another holes, right? So from that we get the static pressure of the flow. Right? So we also call it Prandtl-Pitot static flow. Right? Right. So based on this uh, value of this static pressures and the stagnation pressures, right? So based on that, we can also calculate the velocities of the flows, right? From this uh, Bernoulli's equation, right? Right. So these probes are used for both subsonic and supersonic flows, right? But in case of supersonic flows, because because it's a supersonic flow and we receive a shock in front of the probe, right? So that effect has to be taken into consideration, and accordingly calculations have to be done, right? Whatever data the probe provides, so it has to be processed accordingly, right? Yes, so from the probe's data we can measure the velocities also, right? So this was about temperature measurement and then pressure measurement. Okay. Now there is one more property in the flows, that is density. Right? In the compressible flows, because of the compressibility of the flows, right? There are density variations that the flow encounters. So to study those variations, right? So what we do is we do it qualitatively, right? So we have a few techniques, right? Based on those techniques, we develop our instrumentation, and then we try to visualize those variations, right? So these, I believe, these visualizations for me are very fascinating, right? So, so if somebody of you in future does some experimentation across such instrumentation, right? Okay, so this is lecture 27, right? Here, the first topic is density variation techniques. So, as I was discussing that we qualitatively we document the flow, right? The variations in the flow. So the different techniques that we use for that. So that has been discussed or introduced, I should say, in the uh, few slides, starting few slides, right? And then the principle of optical instruments has been given, which fundamentally is the change in the refractive index of the flow, right? So be it gas or something else. So in that case, because of the density variations, there is change in the refractive index. So this change in refractive index, because of this change in the refractive index, it makes the light ray to bend in a way, right? And this bend of the light, we exploit this uh, this behavior of the gas, right? When there are density variations, and based on that, we develop our instruments, right? Right. So this is about principle of optical instruments, right? So in that series, right, in that topic, we have three such techniques, right? One is Schlieren apparatus, right? And then there is shadowgraph technique, right? And then there is interferometer, right? And later also there is this electric discharge flow visualization, right? So these four topics have been discussed, right, in detail in the lectures, right? So later, from the questions based on these topics, we shall discuss these topics, right? Okay. All right. So then there was this last lecture of this week. So it was majorly on subsonic flows, right? Measurement of subsonic flows. So we use in uh, sorry, in laboratories we use subsonic wind tunnels for that, right? So so how the instrumentation of such wind tunnels is done. So this has been given in detail in the lecture, right? In this lecture. So there are different types of pressure probes, right? So there is a single channel pressure scanner, right? There is pitot static probe. So we have discussed so pitot static probe, right? And then in here in IIT Guwahati, there are this these facilities are there. Instrumentation is concerned, or the type of setups that are in use in the study of subsonic flows, right? So here we have this 16 channel pressure scanner also, right? So there are 16, so it can handle 16 channels at a time, right? Then there is this very sophisticated instrument that is a hot wire anemometer, right? So in this instrument, we basically use a very thin wire, right? Very thin wire is placed in a probe, right? The thickness of this wire is in micrometers, right? So when this wire comes in contact with the flow, so it's because of change in its temperature, its resistance changes, right? So that change based on that change, we find out. So what is the velocity of the flow, right? So this can be done using this instrument. And then there is this 3D traverse system, right? So 3D traverse system is basically when we are trying to place a probe in the test section, right? So if we want to move the probe in the test section, so how do we mechanize it, right? How do we automate it, right? So in that case, we use this 3D traverse system, right? Okay, all right. So then we have a lecture. Oh, okay. So this is of this lecture only. So there are other facilities also, like six component force balance. Six component here means we can measure the forces in three axes, right? So there is in the longitudinal directional, in the lateral directional, and in this vertical direction. Forces can be measured, right? And then there are three moments in the three axes, right? So one is for yaw, right? And one is for this rolling, and then there is for pitch also. Sorry, one moment is for pitch. So these six measurements we can take based on this force balance, right? And in the subsonic wind tunnel, then we have visualization techniques like smoke visualization technique. So IIT Kanpur has a very good facility of this smoke flow visualization that I also have visited, right? Then there is this laser sheet flow visualization, right? So which is also used in PIVs, right? Which is a state of the art flow velocity measuring technique, right? So the IIT Guwahati also has this flow visualization technique, right? And then there are 3D printers, very common in research in these times, right? So to fabricate your model, you can use these printers, right? Scaled models, right? Then the performance and characterization of these subsonic wind tunnels has been discussed, right? And then at last, there is research that is going on subsonic wind tunnel, right? So this way, we have done the topics discussion for this week. Now we shall move on to the questions, right? All right. So the first question in front of us is based on measurement challenges in compressible flow, right? So question number one says, pressure gradients can only lead to change in velocity of the flow and not its density, right? So, so the options to this question are whether the statement is true or false, right? So if we see the discussions we have done in previous sessions, So if we see the nozzle flow, right? So there was also this concept of back pressure, right? So based on the pressure in the reservoir, right, and the pressure at the exit, based on that gradient, we were making our flow to accelerate, right? There we see that in cases there are shocks in this divergent section of the nozzle, right? And the flow is also sonic at throat, right? At times. So if the flow is sonic, it means the flow is uh, compressible, right? Because beyond this Mach of 0.3, the flow is compressible. So that means that the pressure gradients do lead to change in the density, right? So if the pressure gradients are making flow sonic or supersonic, right? So which essentially means that it is leading to compressibility of the flow, which is nothing but change in the density, right? So if the statement says that pressure gradients can only lead to change in velocity of the flow and not its density, then it's a false statement, right? Okay, then. So we have next question in our hand, right? So this question is based on temperature measurement, right? Question number two. The question says that the total temperature in a flow is measured by a device without disturbing it, right? So the total temperature in a flow is measured by a device without disturbing it. So whether this is true or false? Yes. So as is done in the measurement of pressure sensors, pressure data, right? Here also, when we are trying to measure a uh, property, a total property or a stagnation property, in that case, we need to protrude the sensor or probe in the flow, right? Just by, I believe I should draw this, right? So if you see, so this is our flow, right? So when we want to measure the static, let's say we have flow in this direction. So when we want to measure static property, right? So in that case, we do not disturb the flow, right? As we know, there are two components of a property, right? So one is static and one is dynamic. Dynamic is by the virtue of the flow, right? And then there is inherent part of that property that is static, right? So, so if we just want to have the static part, right, the inherent part, so in that case we place the probe on the wall, right? We don't want the total the stagnation value of that property, right? But then if we want the stagnation part, so for as we were doing for pressure sensors for this pressure data, right? So something like this we were doing. We were just keeping the probe in the flow, right? So same we do for the temperature measuring probes, right? Which have a thermocouple installed at the tip of that probe, right? So in that case, we need to place that probe in the flow, right? So yes, right. So if the statement says that the total temperature in a flow is mm, measured by a device without disturbing it, right? So that statement would be a false statement, right? Because we need to place it just to have a sense of like how the placements of the mm properties measuring probes is there in the real experimental setups, right? This question tells us that, right? So this would be in that case a false statement, right? So you'll have to disturb the flow. Great. So, so the next question is on temperature measurement, right? Question number 3. And it says that a thermocouple is based on which of the following options? And the options are these. First option is D'Alembert's principle. Then second option is Seebeck principle. Third option is superposition principle, and then fourth option is Faraday's principle. So I have already given answer to this question, but we will discuss, right, this particular effect. Right? So now what happens is we have two junctions, right? Or two junctions or two spots you call, or two places you call, right? So in these two junctions, one has to be a reference junction, right? So let's say the second one is I'm just drawing a schematic, right? So the second junction is the reference junction, right? So reference means that the temperature at this junction we know, right? And in the temperature we are interested in measuring, right? Sorry, is here, right? So there are two temperatures. One is a known temperature, right, at junction 2, and one is an unknown temperature at junction 1. Right? So in any case, when there is difference of temperatures, right, at these two junctions, in that case, there is flow of heat, right? Let's say this is the track of heat, right? In that case, this is a higher temperature, right? Junction 1 is a higher temperature and junction 2 is a lower temperature. In that case, there is this flow of heat, right, from junction 1 to junction 2. In case the temperature, in case the materials used for these junctions are same, right? In that case, this yes. So what happens is, in that case, in any case, there will be development of electromotive force, right? Which basically gives this voltage change, right, across these two metals, right? Yes. But for thermocouples, we prefer that uh, metals that we are using in the junctions, they are dissimilar, right? In that way, the direction of the heat and this mm, current, right? The direction of the heat and the current are opposite, right? So if in this case Q is this, so if the materials are different, in that case the direction of I will be in this direction, right? So this is our Seebeck principle, right? And based on this data, we get to know the temperature of uh, interest, right? So what we do is we initially we calibrate junction 1 with some known temperature. We have junction 2 already. Then we with some known temperatures we calibrate this thermocouple, right? We will keep one known temperature here, then another known temperature here, then another known temperature here, right? And then we get a trend of the behavior of this probe, right? And from that trend, the trend basically is an equation, right? A linear equation in cases, right? So based on that, we have the voltage data of the thermocouple, right? So when we in our flow we keep this thermocouple, right? This thermocouple gives us some voltage, right? And now we have calibrated the thermocouple. We had already calibrated the thermocouple based on the known values of temperature, right? And we have a this uh, line, right? Equation of line, right? In this equation, one axis is voltage and one axis is temperature, right? So we have this equation on voltage and temperature, right? And the uh, probe, when it is in flow, it will give us voltage, right? And this voltage uh, data we put in this equation of line, right? So this when we put this in equation of line, in that case it will give us a temperature value, right? Which is the temperature value we were trying to measure, right? So in this way we use a calibrated thermocouple to measure the temperature data, right? All right. So this is basically a function in temperature and voltage, right? And from that we get our required temperature value, right? Okay. So this is Seebeck principle, right? Then next question we have again is on temperature measurement, right? So the question says that uh, in a thermocouple, one junction has the temperature to be measured, right? While the other has a known temperature, right? So I have already discussed this, right, in detail. Right. So we have one value that is to be measured, and then we have a reference value that is known temperature value, right? So this statement is correct, right? Okay. Right. Then we have a next question, right? The question number 5 on temperature measurement again. And the question says that which type of thermocouple is developed using chromal and constant 10? So this is a fact-based question, right? Which is to be remembered, right? This is totally based on remembering, right? So though there is no core concept in such type of questions, but such type of questions do come in exams, right? So that's why this question is here, right? So which type of thermocouple is developed using chromal and constant? Right? So this has been given in the uh, one of the slides of this week's content, right? So it's in lecture 26. So different type of thermocouples are there, right? So E type is a chromal constant, right? K type is a chromal allumal, right? One interesting fact about these thermocouples is that, or one interesting fact is that these one such thermocouple is also developed in our gas dynamics laboratory, right? One of my seniors uh, is working on the development of a thermocouple, right? So I believe she's using this chromaland constant, if I'm not wrong, but I'm not sure. But I believe she's using chromal definitely. But then next, the second metal what she's using, I'm not sure of. Okay, so if we see our question, Cromwell Constantin. So we have E-type and right. So this is A answer comes out to be the correct one, right? Right. So I have mistakenly given D as the answer, but A has to be the answer to this question, right? So it's already 1 hour, right? Since this session has started, so we shall take a short break of 5 minutes and then we shall continue with today's session. Thank you. Okay, so we will continue with our session, right? So next question in our hand is based on Prandtl number, right? So I have discussed Prandtl number and the topics. So question number 6, when the Prandtl number is low, the temperature observed by a thermocouple is higher than the actual temperature. So first of all, let's see what a Prandtl number is, right? This is basically the measure of uh, thermal diffusivity, right? So this is ratio of thermal diffusivity to the viscous effects, right? So uh, nu represents the thermal diffusivity and the A represents the viscous effects, right? So when the Prandtl number is low in that case, which means that the thermal diffusivity is low, right? Or the viscous effects are high, right? So in that case, the statement says the statement says that the temperature observed by a thermocouple is higher than the actual temperature. All right. So what happens is when the Prandtl number is low, right? In that case, if you see your uh, lectures content, right? So when the Prandtl number is less, which means the heat conduction from the surface dominates, right? And the probe feels temperature less than the stagnation pressure, right? So in that case, what happens is the temperature observed by a thermocouple is less than the actual temperature, right? So if this statement says that the temperature observed by a thermocouple is higher, in that case, this is not a correct statement, right? And even if you see the temperature profile in such cases, right? So Prandtl number is low for what materials, right? For air, Prandtl number is 0.7, which is a low value, right? And for water, the Prandtl number is 7, right? So it means thermal diffusivity in case of water is pretty nice, but at the same time for air, which is very poor, right? The thermal diffusivity is very poor. So the temperature of the flow in actual and what the thermocouple is giving, there is a difference in that, right? So the thermocouple gives a lower value because of this poor thermal diffusivity, right? Okay. So this is our question number 6, right? So it gives a lower value. This is a false statement. So moving on to next question. So this question is based on density variation techniques, right? So as I was discussing in the topics, so density variation techniques are mainly to have the qualitative feeling of how the flow density is changing, right? So for that we use techniques like Shuttlegraph technique or Schlieren setup, right? Or interferometer we use, right? And then one more technique is there, this electric discharge flow visualization is there, right? Sorry. All right. So question number 7 says that variation in density of a gas stream produces a corresponding change in the refractive index of the gas. Right. So whether this is true or false. So these questions are from lecture number 27, right? Yes. So as I was discussing in the topics, that change in the density leads to change in the refractive index, right? Refractive index is nothing but the ratio of the density of uh, a medium of focus to that of the density of the medium of focus to that of the density of air, right? So this is basically what a refractive index, sorry, refractive index is, right? So with the change in the density of the gas, obviously there will be change in the refractive index of the gas, right? Because it's the ratio of densities, right? With respect to the density of air. Right? Right. So based on these changes only, what we do is we develop our instruments. Right? So when there are such uh, changes are encountered, right? So if you see, this is question number 7. So there are three parameters, right? So one is time, right? The time the light ray takes to reach a particular destination or screen, right? So it changes, right? And then also there is displacement. So without the change in the density, if a ray of light has a particular path, there will be uh, after deflection there will be change in the location, right, of the ray of light on a particular screen. So that displacement can be a parameter, right? And then there is this deflection angle, right? The angle with which the ray of light deflects, right? So these three things are there, right? Based on which we can develop our uh, setups, right? To visualize the density variations. So this answer to this question is obviously true, right? But it's essential that we, though the question is very straightforward, very simple, but it's the discussion corresponding to the question is very important, right? It gives a lot of info with respect to the concept that uh, is there in the question, right? Based on which there is question, based on which the question has been asked, right? So based on that, various questions can be framed based on that. So the idea is that we should have a great hold on the concept, right? Okay. Then moving on to the next question. Okay. So the question says that the question is on principle of optical instruments. And the question says that the Schlieren apparatus is useful in studying the density gradient, right? So this is correct. So up to this point, the statement is correct. The Schlieren apparatus is useful in studying the density gradient by measuring displacement of the light ray. So whether this statement is correct or not. Okay. So let's first of all draw the Schlieren setup, right? So in the actual supersonic wind tunnels, so what we do is, so let us suppose this is our tunnel, right? This is our tunnel, right? And here we have our window, right? So this is our window, right? So what we do is the setup is in such a way that one component is here, right? one source of light is here at point A. From there, this light source uh, gives light towards this window, right? Glass window. And then at this point, we have our screen, right? On which we get our uh, image, right? Which is nothing but a camera, right? Where we capture our frames, right? Now, if we see in this lateral plane only, so how the setup looks like. So it is as follows, right? So it is like this. We have this source of light, right? Then we have this, right? First of all, using a lens, right? We direct the uh, light towards a slit, right? The purpose of the slit is to control the amount of light that we want to propagate, right? Towards the test section, right? And then this light, what we do is this light by means of another lens, we channelize towards the test section, right? Now here is our test section, the test section I was talking about, right? Above. The test section I was talking about, right? Then here, from here, the light exits, right? And then again, we use a lens to focus it, right? On a screen. This is our screen. And here we keep our knife, right? So this is the Schlieren setup. Right. So whenever there is a, change in the density in the flow, in that case, so this there is deflection in this particular lens, right? So they go like this, or something like this. And based on these changes, somehow we visualize our flow, right? So such facility is also present at the supersonic wind tunnel facility of BIT Mesra, right? From where I have done my master's in aerodynamics. So my topic there was on subsonic problem, right? But then they have pretty nice facilities of wind tunnels. They have a subsonic wind tunnel and also two supersonic wind tunnels of different restrictions, right? So there they have this Schlieren apparatus, right? And they also perform the shadowgraph technique also they use there. So basically, when we are using a Schlieren apparatus, so we see the this change in the angle of the light ray, right? So the way the light ray has changed its direction. So Schlieren apparatus is basically based on that, right? So in that case, this statement becomes false, right? All right. So moving on to next question. The question again is based on principle of optical instruments, right? And the question says that an interferometer is useful in getting the density change from the information of deflection angle of the light array, right? So that is not true, right? Because we have just discussed that an interferometer or a Schlieren setup, right? In that setup, we based on the deflection angle of the light array, we take our data, right? But in case of interferometer, that is not the case, right? So here, what we do is based on the this displacement of the light array, we develop our setup, right, for the interferometer, right? So this is something like this. So if this is your flow direction, right? And let's say this is your screen, right? In that case, if originally your light was in this direction, right? And it has deflected to this direction, right? In that case, this angle with which it gets deflected, this is used in Schlieren technique, right? And the displacement, sorry, related to this deflection, that is dz, this is used for interferometer, right? Setup. Right. This is also false, right? And the information of displacement. Then the sorry, then the next question here is based on Schlieren apparatus, right? So Schlieren technique can give a quantitative estimate of the density gradients in the flow field. So this is obviously a false statement because we visualize the flow field based on the Schlieren apparatus, right? Okay. Right. So next question again is on shadow graph technique, right? And the question says that in shadow graph technique, the variations in illumination of the picture on the screen are proportional to first derivative of the density, right? So whether this is a correct statement or not. So let's first of all draw the schematic of the setup, right? Right. Let's say flow is coming from this direction, and we have placed our aerodynamic body here, right? Somehow, right? And we are visualizing the flow around it, right? Or the density variations around it. So in that case, obviously this section is a glass window, right? This is also a glass window. These are glass windows. In the above setup also, in these are glass windows, right? Only then light will pass through it. So it's simpler than the Schlieren technique, right? So here we have a source of light, right? And then a lens, right? A collimating lens, right? And then we have a screen, right? So for for the lab purposes, we because we have to store this data somehow, so we use a camera for that purpose. Same is the case with the Schlieren technique also, right? So here we have a source of light, right? A lens, right? And which uh, through which the light straightens and passes through the object, right? And then we see it in a screen, right? And the density variations that take place as the flow moves across this object, right? Passes this object, so that we can capture in the screen or camera, right? Right. So one difference between Schlieren technique and shadowgraph technique is that so the variations on the screen, right? The density variations are these are proportional to this. For Schlieren technique, it's for first derivative of density variations that we get to see in case of Schlieren techniques. And in case of shadowgraph technique, we get to see the second derivative of density, right? So this is our shadowgraph technique, right? The shadowgraph technique also is cheaper or less expensive in comparison to Schlieren technique, right? Because a lot of components have been um, removed, right? if we compare it with the Schlieren technique. There are commonalities in both the techniques, right? But then in shadowgraph technique, a lot of things have been taken out if we compare it with the Schlieren technique, right? And as far as our question is concerned, so because it has written that the this illumination of this picture on the screen is proportional to first derivative, that is not correct, but it is proportional to the second derivative, right? So it's a false statement. Also, this uh, to know like what do we mean by first derivative, or what do we mean by second derivative of density, and how do they relate to um, illumination of the picture, right? For that, it's better that we refer to some reference, right? Or you guys refer to some reference to get a clear picture on this question, right? Same is the case for Schlieren technique, right? Uh, so how the this order of derivative, right? Or the yes, how the order of derivative is relating to different physical parameters. So for that, it's better that you guys refer to some reference, right? It will give a more clearer picture. Great. So moving on to next question. So the next question says that next question is on subsonic wind tunnel, and the question says that question number 12. One of the works of a settling chamber in a subsonic wind tunnel is to reduce the turbulence on the flow, right? So first of all, let's draw. So the wind tunnels can be either sorry can be either open circuit wind tunnel or a closed circuit wind tunnel, right? So I'll draw a open circuit wind tunnel, right? An open circuit wind tunnel that is present at the at one of the labs of IIT Guwahati, right? So the components of a wind tunnel are subsonic wind tunnel, open circuit, right? Because the flow is not circulating here, it's coming from one direction and exiting at this direction, right? So how there is a flow in this wind tunnel is that at the drive section we have a fan, right? So it sucks in the air, and this way there is a flow in the subsonic wind tunnel, right? And starting with the settling chamber, right? So it has this honeycomb-like structure inside it, right? If you see the front of this, sorry, I should not draw it in this section. So if you see the front of this, so it is like this, honeycomb, right? The purpose of this structure is to, first of all, straighten the flow, right? So that there are no circulations, right, in the flow. Also, if there is some turbulence in the flow, in the air that is entering the tunnel, in that case, so to reduce the turbulence of that air entering the tunnel, right, and to better channelize the flow, for that this honeycomb structure is used in the settling chamber, right? And then there is a contraction zone to speed up the flow, right? And this contraction zone ends at the test section, right, where we keep our model, a scaled model that we wish to study, right? And then to uh, for the air to exit the wind tunnel, we have a diffuser, right? So that there are pressure losses are not high, right? As the air exits the wind tunnel, right? So this way, if we see our statement, it's true, right? The one of the primary functions of a settling chamber is to reduce the turbulence in the flow, right? The next question is on a instrument used to measure velocities, right? The hot wire anemometer, right? That I have briefly discussed in the topics. So the hot wire anemometer is based on which of the following, right? So we have done experiments on this when I was in BIT Misra, right? So the hot wire anemometry is based on King's law, right? So basically, it's an equation, right? And using this equation and data from the hot wire anemometer, we can figure out the velocity of the flow. Okay, so this is about hot wire anemometer, right? Also, the welding part of this probe is quite tricky because the wire, as I was telling, is very thin. So to weld it on the probe, it's a task, right? So you need to use proper lenses to see this thin wire, right, in micrometers, and then to spot weld it on the probes. So it's quite a bit task, right? All right. So we are done with the conceptual type questions, right, for this session. Now we are left with two numerical type questions, and then we are done with today's session. All right. So this question says that the temperature of a supersonic flow, right, measured by a total temperature probe is 570 K, right? The probe is having a recovery factor of 0.95, right? The Mach of the flow is 1.6. The isentropic properties static to total temperature is 0.718, right? Calculate the static temperature. So, oops, sorry. I already gave the answer, but yes, by mistake, but let's work it out, right? So we have been given from the probe, the temperature we have is 570 Kelvin, right? And then recovery factor is 0.95, right? Mach is given as 1.6, right? And static temperature to total temperature is given as 0.8047, right? Oh, sorry. It should have been 0.8047. All right. Okay. So if we see K is what? Tp minus T infinity divided by T naught minus T infinity, right? And K is 0.95 equals to 570 minus T infinity divided by static is T infinity divided by T, oh, sorry, 0.8047 minus T infinity, right? So if we work this out, this comes out to be 0.95 T infinity minus 0.8047 T infinity, which is equal to 0.8047 into 570 minus T infinity, right? Which is nothing but yes. Yes. So we can subtract this, and what we get is 0.1953 T infinity into 0.95, right? Equals to 458.679 minus T infinity, right? Implies right. Yes. So T infinity terms will take to one side, right? Plus 0.8047 T infinity equals to, yes, 458.679, implies T infinity equals to 463.202 Kelvin, right? Right. So this is our answer range. And now if we see the last question of today's session. The question says that a pitot tube is used to measure the velocity of an airstream, right, at 25 degrees Celsius and this temperature. If the velocity is, then the dynamic pressure is. So we know that the dynamic pressure is P naught minus P infinity, half of rho V square. V here in the question is given as 4.4, right? But the rho is not given. So what we will do is we will use perfect gas equation, right? R is given 287 and temperature we have 25 degrees Celsius, which is in Kelvins 298, right? So implies if we work out the density, it comes out to be 1.1847 kg per meter cube, right? Right. So in that case, the dynamic pressure half of 1.1847 and then 4.4 square, which is 11.4678, 11.47 Newton per meter square, right? So this was our last question of today's session, right? Also, yes, so between 11 and 12, also we are out of time, right? It's already 8:01, right? So we shall, in conclusion, say that we discussed topics briefly of week 11's content, right? And then we discussed 13 conceptual based questions based on the uh, experimental techniques for measuring pressure, temperature in compressible flows, and then visualizing the density variations using techniques like shadow graph technique and then Schlieren setup, right? and then interferometer we used, right? And after discussing the conceptual questions, we did two questions, numerical based questions, right? One was on measuring the or calculating the static temperature based on probe recovery factor, and then last numerical was on measuring the dynamic pressure, right? So this way we conclude today's session, right? And for the next and the second last session, right? We shall meet on Sunday, that is 14th of April, right? From the session will be from 3 to 5 p.m., right? Till then, I'll say goodbye and happy learning, right? Thank you.